one. Good day, grade 12 learners. Welcome to today's physical sciences lesson. My name is Thandwe Uwane. This lesson is brought to you by the Gauteng Department of Education in collaboration with Saibono Discovery Center. You can also interact with us on our WhatsApp line, which is 064 748 8913. I repeat, 064 748 8913. Today we are going to look at a chemistry lesson, which is our paper 2. The lesson on our examination paper is going to be question number 5. So question number 5 deals with the rate of reaction. We are going to look at the factors that affect the rate of reaction and also to look at how can those factors affect the rate of reaction using the collision theory. Now, according to the lesson objectives, the first thing that we are going to do, we are going to define reaction rate. You know that in physical sciences, before we start interacting with every term or definitions must be there so that you can understand what is it that we are going to talk about. We are also going to calculate the reaction rate from a given data. So we are also expected to do some of the calculations, even though there are no many calculations as we expect them to be like in physics part. But here we are going to calculate the rate of reaction and the data will be given to us in order for us to calculate the rate of reaction. The factors that affect the rate of reaction, as the exam guideline says, you must list them, but we know that we are not going to list the factors, but we are going to say how are the factors affecting the rate of reactions, and we are going to focus on how are the factors affecting the rate of reaction using the collision theory. We are going to explain in terms of collision theory, as I said, the various factors that affect the rate of reaction. After understanding which factors that affect the rate of reaction, then you need to explain using collision theory on how each and every factor affect the rate of reaction. We are also going to interpret data. Data can be in the form of tables or graphs on different experimental techniques for the measuring of the rate of reaction for given any reaction. We will also look at the definition of a positive catalyst and also interpret the graphs of distribution of molecules energies using the Maxwell-Boltzmann curve. And you must know that always when you are given a data, you must know how to explain using the data that you are provided. So as we are going to be given tables and also as we are going to be given graphs, we must be able to interpret them in order for us to respond to the questions on question number 5. Now we know that this topic started last year in grade 11 where we're looking at types of reactions. We know that we have two types of reactions, which is exothermic and endothermic reactions. Now, what do we mean by exothermic and endothermic reaction? We know that when we look at exothermic reaction, we look at the reactions that releases energy. In a reaction whereby you have a thermometer that you are measuring the heat of the reaction, if the thermometer rises, it is an indication that energy is being released. However, if the thermometer drops, it's an indication that energy is being absorbed. So we know that when we talk about an exothermic reaction, we talk about the release in energy. So it means you can find some heat being liberated during that reaction. And also we know that definitely we are going to look at how are the particles responding when the certain factor is affecting the rate of reaction. So that is why we are going to also look at the kinetic energy of particles. When we look at kinetic energy, we know that kinetic energy is the energy an object possesses as a result of its motion, is the energy of motion. So these are the terms that we will be using as we are explaining some of the factors that affect the rate of reaction. We also did bond energy in grade 11, bond length and activation energy. Let's recap on what is bond energy. Bond energy is the energy needed to break one mole of its molecules into separate atoms. I think we know that we know what are atoms. Atoms, we find them on our periodic table. There are different atoms in the periodic table with different atomic numbers that indicates the number of protons of each and every atom. So we are going to look at bond energy, and we are going to look also at the bond length, because remember, as we are going to look at the chemical reactions, we will expect particles to react. So we look at the average distance between the nuclei of two bonded atoms. As different atoms are going to come together to undergo a chemical reaction, we expect to see how far is their nucleus from each other as they are going to react. And then we know that for any reaction to occur, we need activation energy. There is no way that a reaction can occur if the activation energy of that particular reaction is not sufficient. What is this activation energy? Is the minimum energy needed for the reaction to take place. So we expect that for every reaction to occur, it must at least have the sufficient activation energy that will allow the interacting particles to undergo a chemical change. We also look at the different graphs of endothermic and exothermic graph, and in grade 11 we also labeled the graphs. This one is a graph of exothermic reaction. So you need to know how do you calculate the enthalpy of a reaction, and how do you identify the activation energy of the reaction. So this is an example of the exothermic graph, and the opposite is endothermic graph. So we need to go back and remember, because this is also an examinable concept that we took from grade 11 in terms of what is the difference between an exothermic graph and an endothermic graph, and not forgetting that definitely there will be those activation energy that will be needed for the reaction to take place. Now, what is a chemical reaction? I think it is very important to understand what is a chemical reaction before we can start and look at the factors that will affect the rate of reaction. And in all the factors that we are going to look at, we will only focus on the factors that will increase the rate of reaction. So we are not going to look at the factors that will decrease the rate of reaction. However, all the factors that we are going to look at will make sure that they increase the rate of reaction. So a chemical reaction is the process in which reactants are converted to products. We know that initially when you start a reaction, you are going to have the reactants. And as the reactants are reacting or are bonding with each other, we are going to form products. So initially we know that we don't have any product. Our product is 0. However, as the reaction occurs, we will start and have products of that specific reaction. And during chemical reaction, existing bonds between the reactant particles must be broken and new bonds must be formed. Because if the bonds are not broken down, it means there are no new bonds that will be formed. So to say you have undergone a chemical reaction, there must be bonds that are broken so that new bonds can be formed. And particles of different reactants must do what? Must collide. And definitely the collision must be effectively. So we expect that whenever we are undergoing a reaction, if the reaction is successful, it is because there is an effective collision of reacting particles. And we know that they need a sufficient energy, which is known as activation energy, for the reaction to occur. So as we said, that activation energy is the minimum energy required for the effective collision. So if you will need to undergo a reaction and you need the reaction to be successful, it means we must make sure that particles collide effectively with each other for the reaction to occur. The particles cannot just collide. They can collide sometimes, but if the collision is not effective, then it means that reaction will not occur. Now, as we said that we need to define a reaction rate. What is a reaction rate? The rate of reaction is the change in the concentration of reactants or products per unit time. The change in the concentration of the reactants or product per unit time. I think it is important to know how will the concentration of the reactants change and how will the concentration of the product change as we are looking at the reaction. We know that products are always used for them to form, the reactants are always used for them to form what? Products. So we need to know that if the reaction is occurring, what will happen to the product? We will definitely expect that the reactant concentration will decrease and the product concentration will increase. Remember, as the reactants are reacting, we expect their concentration to decrease. And as the products are being formed during the chemical reaction, we expect the concentration of the products to increase. And we are also going to calculate the rate of reactions. If we calculate the rate for the reacting particles and we look at the rate of the reactants, we will expect that average rate be equals to the change in the number of moles over the change in time. But we are going to put a minus sign when we calculate the rate of the reactants. Why are we putting a negative sign when we calculate a rate of the reactants? We know that reactants concentration decreases because reactants are being used. Therefore, when we calculate the change, we know that we always say final subtract initial. Therefore, it means now the number that we are going to get at the final reaction, or at the end of the reaction, will be smaller than the number when the reaction starts. Therefore, the negative sign will assist us to get a positive value as we are going to calculate the rate of reaction. So the negative sign is only used when you calculate the average rate of reaction of what? Of the reactants, because we know that final subtract initial is going to give us a negative value. So the negative, we use it for that instant. However, when you are calculating the average rate of the product, you are not going to include a negative sign, because we know that we are going to start our product at 0 and will end at a certain number of moles or mass or volume. It depends what is it that you are calculating. Therefore, we don't include a negative sign when we calculate the rate of the product. And what you must understand also is that the formula of the average rate is not part of your data sheet, and also the formula of the average rate doesn't qualify for any mark, because you can calculate any average rate of any molecule or any substance. Now, the number of moles are increasing as the product is formed, so the value definitely will be positive. So that is the reason why we don't include the negative sign when we are calculating the average rate of the product. Now let's look at our collision theory. We agreed that for the reacting particles, there must be an effective collision for them to. So there are conditions for the effective collision, because if collision must be effective, number one, what will make the reacting particles to have an effective collision? The particles must collide with minimum energy that is equals to or higher than the activation energy for them to start the process of breaking or forming the bonds. So this is the condition that is needed for the effective collision. We need minimum energy that is sufficient for the reaction to occur. So we are saying there will be a minimum energy that is equal to or higher than the activation energy for the reaction to occur and for the collision to be effective. Number two, the reacting particles must collide with correct orientation that can lead to the rearrangement of atoms and formation of the product. So also there must be correct orientation of the reacting particles for the collision to be effective. So these are the two conditions that are required for the reaction to be, or for the particles to collide effectively. Now, these are the factors that affect the rate of reaction. We said that the exam guideline says you need to list the factors that affect the rate of reaction, and we are going to look at how does each factor affect the rate of reaction, explaining it using the collision theory. So we have concentration. We know that concentration can affect the rate of reaction, concentration of the reactant, especially when we talk about solutions. So how is concentration affecting the rate of reaction? We will look at how is concentration affecting the rate of reaction and also explain it in terms of the collision theory. Also, the surface area of the solids of reactants, which is the state of division. we know that as we are going to deal with some of the solids that will undergo a chemical change, we'll need to know how will the surface area of those solids affect the rate of reaction, and also the pressure if the reactants are the gases. We know that pressure always affects gases. So what will happen if there's a change in pressure in the rate of reaction? Temperature of the reacting mixture, which is also another factor that can affect the rate of reaction. Nature of reacting substances. Also, it depends on what is the phase of the reacting substances, and we'll look at the phase and also give a conclusion to say how can it affect the rate of reaction, and adding of a catalyst or adding of a suitable catalyst. So all what I just mentioned are the factors that affect the rate of reaction. Now let's explain how does each factor affect the rate of reaction. We will start with our surface area. Remember, we said surface area is only a factor that will affect what? Solids in as our reactant. So we say here the increase. So as the rate of reaction increase with the increase in the surface area. How do we increase surface area? When you have a solid, let me just make an example of a chalk. When you grind it, or when you grind a tablet, you are increasing the surface area of that tablet. Therefore, it means it will make the reaction rate to be higher. It will increase the rate of reaction. Now, according to collision theory, what is it that is happening as we are increasing the surface area? How can a surface area make sure that the reaction rate is higher? When you are increasing the surface area, you are increasing there will be more reaction sites in that specific solid. So an increase in surface area of the reactants results in more reaction sites. That is the first thing. And the second thing is that there will be an increase in the number of reaction sites and the increase in the frequency of total collision. So we expect more particles with sufficient kinetic energy that is greater than or equals to activation energy. Remember, this is one of the conditions that is needed for effective collision. So there will be more particles with sufficient kinetic energy that is greater than or equals to activation energy, and there will be more effective collision per unit time. Therefore, the reaction rate will increase. So when you are responding in terms of how does each factor affect the rate of reaction, I think it is very important to use a bullet form so that you make sure that all the facts are covered as you are explaining the collision theory. So we started by saying, how will the increase in the surface area affect the rate of reaction or increase the rate of reaction? We expect to have more reaction sites. We expect to have more particles with sufficient energy that is greater than or equals to activation energy. And we also expect more effective collision per unit time. As a result, the reaction rate will increase. So we are saying the most effective way to increase the surface area of a solid is to grind a solid into a powder. So we need to also know how can we increase the surface area of a reacting substance. The second factor that we're going to look at is the concentration. Now, what is it that a concentration can mostly affect? We know that a concentration can mostly affect what? The solutions, because concentration of all solids is 1. So therefore, concentration is the measure of the number of moles of dissolved solute per unit volume. So the higher the concentration of a reactant solution, the higher the reaction rate. So we know that when you look at the concentration and you look like the concentration of a solution is increasing, we expect also the reaction rate to increase. Now, how does concentration affect rate of reaction using collision theory? The increase in the concentration increase the number of solute particles per unit volume. So we know that when we calculate the concentration, we normally see is equals to N over V, which is the number of moles per unit volume. So when you increase concentration, you are increasing the number of particles per unit volume, and there will be more particles with sufficient kinetic energy that is greater than or equals to activation energy, and there will be more effective collision per unit time. That means there will be an increase in effective collision between particles per unit time, and therefore the reaction rate will increase. So we expect that when you are comparing concentration, the one with higher concentration definitely will have what? Will have more effective collision per unit time, because concentration will increase the number of reacting particles per unit volume. Therefore, it is very important to know how does concentration affect the rate of reaction using collision theory. Then let us look at the temperature. Now we know that the temperature affects the temperature of the entire mixture. Now we must know that the increase in temperature will also increase the reaction rate. Therefore, what is it that is happening with the particles as we are increasing the temperature? As we are increasing the temperature increases the average kinetic energy of reacting particles. So you are increasing the kinetic energy of reacting particles. That is how an increase in temperature affects the particles. And more particles or molecules have minimum energy which is equals to or higher than activation energy. So you can see that the second bullet is common in all the factors that affect the rate of reaction. And also the third bullet, which is more effective collision per unit time, and the rate of reaction will increase. So immediately when you understand the first bullet of the factor, the next two bullets might be the same principle, because we are looking at how can this meet effective collision. So therefore, increase in temperature increase the average kinetic energy of the reacting particles. Therefore, more molecules will have minimum energy equals to or higher than activation energy, and there will be more effective collision per unit time, and therefore the reaction rate will increase. Now, what will happen in terms of adding a catalyst? Remember, we have increased the surface area, we have increased the concentration, we have increased the concentration. However, in this regard, we are now gonna add a suitable catalyst. So adding a suitable catalyst can also increase the rate of reaction. Now, what is a positive catalyst? Remember, this positive catalyst was mentioned on our exam guideline to say we must define what do you mean by a positive catalyst. A positive catalyst is a substance that increases the rate of reaction or of chemical reaction by providing a different or alternative pathway of and lowering activation energy. So when you add a catalyst, you are providing an alternative pathway of lower activation energy. And we must understand that a positive catalyst will not undergo any permanent change during the reaction. So a catalyst does not change the energy of the reactants or product. A catalyst does not affect the heat of the reaction. What it does, it provides an alternative pathway. Alternative pathway of lower activation energy. That is what a catalyst do. It will just lower an activation energy by providing an alternative pathway for the reacting particles. So we are saying, when we explain how does a catalyst affect the rate of reaction, we are saying adding a catalyst will provide an alternative route or alternative pathway, you can say pathway or route, with lower activation energy. And there will be more particles will now react via easier catalyzed route with lower activation energy. So there will be more particles with sufficient energy that is equals to or greater than activation energy, and there will be more effective collision per unit time. therefore the reaction rate will increase. So all the factors that I've just mentioned, they affect the rate of reaction in different ways. So we need to know how does each factor affect the rate of reaction. Now, in terms of the nature of the reacting substance, we know that the medium in which the reacting substances are in will also affect the rate of reaction. So we can look at the properties of the reactants. The rate of the reaction may differ depending whether the medium is aqueous or organic or polar or non-polar or liquid, solid or gaseous. So the reactions in which ionic and polar solutions are involved also takes place at a very high reaction rate. So these are the factors that affect the rate of reaction. Now, when you look at the Maxwell-Boltzmann distribution curves, you can see now that this curve explains the kinetic energy of different particles in different area of under the graph. As you can see that at area A here, few particles with very low energy. Area B, C, and D, most particles with moderate energy. However, when you look somewhere here at this area, there are a number of particles that are having or do not have sufficient energy to react. And also this area represent our activation energy. And only some particles under this portion of the graph will have got enough energy to react. So we need to know the Maxwell distribution curve looking at the three factors which I normally say they are Cape Town, C, T, and P. Okay. Now let's look at the temperature. How does a Maxwell-Boltzmann distribution curve affect is affected by the temperature? You can see that we have graph T1 and graph T2. When you look at graph T1 represent this is the graph whereby the temperature of particles is low. This one represents a lower temperature. However, graph T2 represent a higher temperature. So you can see that both graphs start at the same point. However, as we increase the temperature, the graph will be lower than the first one, and they intersect with one another. And after intersecting, we'll have more particles with sufficient energy that is greater than or equals to activation energy. So you can see that the graph with a higher temperature is dropped and moves slightly to the right, which indicates more particles with sufficient kinetic energy, which is equals to or greater than activation energy. So normally the examiner will say on the same set of axes, show the graph that will represent the increase in temperature. We know that it's going to be lower than the first one, and it's going to move slightly to the right, and it's going to be higher than the first graph when it comes to the end of the reaction at the activation energy area. Then let's look at the concentration. When you look at the concentration graph, we are saying concentration increase the number of particles per unit volume. So when you look at the two graphs, you can see that this one, it was our first graph when the temperature, the concentration was lower. Then when we increase concentration, we increase the number of reacting particles. So the second graph where the temperature concentration is higher will be higher than the first one, and also the activation energy area will also be higher than the first one. So graph 2 is the one that represents a higher concentration, which means that there will be an increase in particles per unit volume. And also there will be, the two graphs will start at the same point, but the one with a higher concentration will end above the first one with a lower concentration. The graph for higher concentration shows the increase in the number of particles whose energy exceeds the activation energy. So you can see that there will be more particles with sufficient energy, which is greater than or equals to activation energy. So we need to know the difference between the graph of temperature and the graph of concentration. Now, when you add a catalyst, we know that a catalyst, its function is to just provide an alternative pathway of lower activation energy. So we need to understand that when you look at this graph, you can see that more particles with not enough energy to react. However, all these particles here have enough energy to react. And originally, only particles under this graph has a higher enough energy to react. So a catalyzed a graph is the one that will show a lower activation energy of reacting particles, whereby there will be more particles with sufficient energy which is greater than or equals to activation energy. So if this activation energy, so there will be more particles with energy that is greater than or equals to activation energy. Now, as we said that when we look at the reaction rate and we define reaction rate, we know that we define reaction as the change in the concentration of reactants and products per unit time. And we agree that the reactants concentration, we expect it to decrease. So here, this is the graph that shows the change in the concentration of the reactant. So you can see that it is starting at a higher concentration and the concentration decrease until the line is straight here. And when the line is straight here, we are saying the reaction has stopped. What makes the reaction to stop? Because a limiting reactant can be used up, or the reactants, because the reactants are used. So the limiting reactant is used up. So when you look at the reactions in question number 5, you know that we are looking at the reactions that are only going to one direction. They are not reversible, meaning that the reactions in question number 5, they stop because they occur in an open system. So when you look at the constant line or at the horizontal line of these reactions, you must know that the reaction has stopped because one of the reactant is used up, or both of the reactants are used up. So this is the graph that indicates the change in the concentration of the reactant. And you can see that the graph is decreasing from a higher value to a smaller value. So that is why if you calculate the rate of reaction, you will see that you will end up having a small value. Let's say maybe this is 0.02 and this was 0.0 or 0.28. So you can see that when you calculate the rate, definitely the answer will be a negative, because this is your final and this is your initial. So that is why I said we're gonna say, if we calculate the average rate, we're gonna say minus the change in concentration of the reactants over the change in time. So the minus will assist us not to have a negative value as we are calculating the rate of the concentration of the reactants, because the concentration of the reactants decreases. However, when you look at the concentration of the product, you can see that the concentration of the product will start from 0 and start to increase until the horizontal line is met, where we also say the reaction has stopped. So the concentration of the product, we know that it increases as the reaction progresses. For all the reaction, you can even see from the previous one, the reaction will start to be faster. The reaction rate will start to be faster. As the reaction progresses, the reaction rate is starting to be lower until the reaction stops. So the gradient of the graph can also determine whether the reaction rate is higher or the reaction rate is slower. We don't say it's faster or slower, but we say is the reaction rate is higher or lower. So you can see that for the first 10 seconds here, the graph is a little bit sharp or steeper to show that the reaction rate is higher reaction rate. As it progresses, it starts to decrease. Here the reaction rate is lower, but here now the reaction has stopped. So even when you look at the graph where you are looking at the graph of the product, you can see that the reaction rate is the gradient of the graph is sharper, but this one you can see is sharper here and more sharper here. And when the gradient is more, it shows that it means here there was another change that occurred, because this gradient here is sharper than this one here. And as the reaction progresses, it becomes low. The gradient, it becomes less steeper, and as it becomes less steeper, it is showing also that there is a lower reaction rate. Here there is a higher reaction rate. So with the steepness of the gradient, you can also see whether the reaction rate is higher or lower. So we say the rate is not constant throughout the reaction. As I said, it changes. The reaction is fastest at the start, gradually becomes slower as the reaction proceeds. From the graph, the fastest part of the reaction is the steepest curve, and the curve of the graph goes flat when the reaction is complete. This is because as the time goes on the volume of the gas that was collected here, it starts to decrease. So we need to know, how do we explain the steepness of the graph related to the reaction rate. So here is the graph that indicates the aging of a catalyst. We know that a catalyst will do what? This is the new activation energy S, and this is the original activation energy. So you can see that now all these extra particles have sufficient energy. As we are adding a catalyst, there will be the sufficient energy that is greater than the activation energy. As we said, a catalyst provides an alternative pathway of lower activation energy. Even when you look at this exothermic graph, you can see that the catalyst will do what? Will lower the activation energy. If this was the activation energy, when you add a catalyst, then your activation energy will be lowered. So this one is an activation energy with a catalyst, and the blue one is an activation energy without a catalyst. Now let's look at how are we going to respond to the question in question number 5 in order for us to answer the questions under rate of reaction. I think when you start answering the questions in question number 5, which is the rate of reaction, you need to collect all the facts that you have done. You need to remember all the definitions like activation energy, definitions like rate of reaction, and positive catalyst, so that you know when they ask you about any definition, you can recall those definitions. And we also said one of the ways to remember the definitions is by you writing the definitions or by you recording yourself in order for you to understand those definitions. Now let's look at this question, which is also under the rate of reaction. They say here the reaction of 15 grams of an impure sample of calcium carbonate, which is CaCO3, with an excess hydrochloric acid, HCl, of concentration 1,0 mole per decimeter cube, is used to investigate the rate of reaction, and the balance equation for the reaction is given. So some of the words that you have on your statement, they are giving you some clarity about the question. Immediately when you see the word excess hydrochloric acid, you know that not the entire hydrochloric acid will be used up during this reaction. So it means also our calcium carbonate is our limiting reactant, as hydrochloric acid will be in excess. The volume of carbon dioxide, because carbon dioxide is one of the products that will be formed as calcium carbonate react with hydrochloric acid. So they say the volume of carbon dioxide gas produced is measured at the regular intervals. A sketch graph representing the total volume of carbon dioxide gas produced as a function of the time is shown below. So this is the graph that shows the collection of carbon dioxide during the course of the reaction. And you can see also that the graph is becomes steeper and more steeper here, and then less steeper. So already we have discussed that when you look at the steepness of the graph, it can tell you whether the reaction rate is higher or the reaction rate is low. So we have the higher reaction rate, and then here the reaction rate is even more higher because the graph here is more steeper, and then here it becomes lower, and then here we know that the reaction has stopped. So in this case, it means our limiting reactant is being used up, and we know that in this case our limiting reactant is our calcium carbonate because hydrochloric acid is in excess. Now the first question says define reaction rate. That is why I was saying before you go and start the question, just gather all the important facts about that question and all the important definitions about that question. So I think the 2 marks of defining rate of reaction, all of us, we need to be able to get it because it's a simple definition that allows everyone to be able to recall it easy. We know that the rate of reaction is what? Is the change in the concentration of the product or reactants per unit time. is not only the change in the concentration of the product or reactants, but we know that is the change in the concentration of the reactants or product per unit of time or per second, which is the full definition of the rate of reaction. They say give a reason why the gradient of the graph decreases between time t1, time t2 and time t3. So when you look at time t2 and t3, yes, we have discovered that the gradient is decreasing. The only way we have a lower reaction rate is because the reactants are being used up. So as the reactants are being used up or are being used in the reaction, definitely the concentration of the reactants will decrease, and as a result, it will also lower the reaction rate. And then it says the changes in the graph between T1 and T2 are due to temperature changes within the reaction mixture. Is the reaction exothermic or endothermic? And then we are saying 1 mark. Let's look at time T2 and T1. When you look at time T2 and T1 and T2, you can see that our graph is more steeper here, and they say it's because of the temperature changes. We know that if the reaction rate is higher, it means there will be an increase in what? In temperature. We know that the higher the temperature, the higher the reaction rate. So it means here the temperature rises, the temperature was increased, and an increase in temperature, of course, we know that it means the reaction is exothermic. So the steepness of the gradient is also telling us whether the temperature was increased or was decreased. But because the gradient is steeper between T1 and T2, it is an indication that the reaction rate is higher. And when the reaction rate is higher, it means the temperature was increased. So the response is exothermic. And in terms of our answer, we can also refer to the steepness of the graph. We can say the gradient is increased, the reaction rate is increased, and the temperature is increased, or energy is released. That's why we are saying the reaction rate is higher because of the increase in temperature. So you need to say what makes you to be convinced to say the reaction rate is higher is because, number one, you have to look at the steepness of the gradient. So if the gradient is steeper or the gradient has increased, then it shows that the reaction is higher. And also, if there is the steepness of the gradient, it shows that the rate of reaction increases because of the increase in temperature. Now they say the percentage purity of the sample is 82.5%. Calculate the value of X on the graph, assuming that the gas is collected at 25 degrees Celsius. Take the molar volume of a gas at 24,000 cubic centimeter per mole. I think the only thing that was left is per mole. So you can see that when we calculate X, our X is the volume of carbon dioxide. So actually the examiners, they say calculate the total carbon dioxide volume that is collected during this reaction. So we know that as we are going to calculate the total volume, what we have is the percentage purity of calcium carbonate, also the mass of calcium carbonate. So we can use the calcium carbonate in order to find the number of moles of carbon dioxide that are going to be formed, because we know that our calcium carbonate is our limiting reactant. So we are going to calculate the mass of calcium carbonate so that we can find the number of moles of calcium carbonate. So we know that 82.5%, which is 82.5 divided by 100 multiplied by the mass of calcium carbonate, which is 15, and we got the mass of calcium carbonate as 12.375 grams. We take the mass of calcium carbonate and we use also the molar mass of calcium carbonate. Remember, CaCO3, which is our formula mass, is going to be calcium is 40 on the periodic table plus 12 of carbon dioxide plus 16 times 3, which is for oxygen. So the total of the molar mass is going to be 100. So we divide by a molar mass of calcium carbonate, which is 100, and then we get the number of moles of calcium carbonate, which is 0.124 moles. And then we are now going to look at the ratio between calcium carbonate and carbon dioxide using our given formula. on the formula, we know that the ratio is, okay, let me just go back. The ratio of calcium carbonate and carbon dioxide is 1:1. So immediately when we get the number of moles of calcium carbonate, we will relate it with the mole ratio of carbon dioxide, and we can see that because the ratio is 1:1, then we can find the number of moles of carbon dioxide. From finding the number of moles of carbon dioxide, we know that N is equal to V over Vm. Remember, we were provided the molar volume of a gas, which was 24,000. And then we are going to substitute the number of moles which we got from the mole ratio here, and we get that the volume of a gas that is collected for the entire reaction is 2,976 cubic centimeter. The next question says, how will the reaction rate change if 15 grams of pure sample of calcium carbonate reacts with the same hydrochloric acid solution? So we know that the purity can also affect the rate of reaction, because the more the pure the substance, the more the larger the surface area. So they say choose from increase, decrease, or remains the same. So, and then use the collision theory to explain that. So we know that as the substance becomes more pure, it means now the purer the substance, the higher the rate of reaction. So we expect the reaction rate to increase, because there will be more particles with correct orientation, and there will also be more effective collision per unit time. So when you increase the purity of a substance, you are increasing the number of collisions per unit time, and there will be more particles with correct orientation. We are going to take just a 1-minute break, and then when we come back, we will continue with how do we interact with different questions in question number 5.
Believe in yourself. Believe a little more in yourself, because to those that believe, nothing is impossible. You have done this before. You have passed your tests before. You have went into a higher grade before. It is possible because you have done it before. Do not doubt yourself. Keep believing in yourself. Keep pushing, because this can be done and you can be great. I want you to ask yourself these 3 questions. Number 1, what do I want? Do I want to become an A student, or do I want to become an average student? Number 2, I want you to ask yourself, how do you plan on getting there? Are you going to put more extra hours, or are you going to just sleep? Number 3, who will be with you in this journey? Because it is important that we associate ourselves with students who have the same vision as us, who want to become a student, who want to put in the extra work, who want to become better at what they do. Unsuccessful people do not plan. They just let life happen to them. But successful people are planning on how they want their lives to be. And right now, you plan on how you want your results at the end of the year to be like.
Welcome back, grade 12s. Remember, you can still interact with us using our WhatsApp number, which is 064 748 8913. We will try by all means to respond to the questions that you are asking, especially during the end of the lesson. Now let's look at some multiple choice questions. We know that multiple choice questions are part of our examination, and it is very important that you know how to respond on the multiple choice questions. This one says the rate of chemical reaction can be expressed in. So now remember, this one is about how do we calculate the rate of reaction. So it says it can be expressed in grams per mole. Yes, it can be expressed in grams. However, it cannot be in per mole. We know that is grams or volume or per unit time, concentration, changing concentration per unit time. So it has to do with any change that a reaction can undergo per unit time. So this one is per mole is incorrect. Even this one is per mole is incorrect. However, when you look at this one, is the change in volume of a gas per unit time Yes, we know that we can expect this moles of a product formed per unit per liter of a solution, which is also incorrect. So in all the options that we're given, we only have one change per unit time, which is number C. So the correct answer for our question is number C. And as you know that multiple choice carries 2 marks, you need to be careful on the options that you are definitely going to choose. When you look at this one, the rate of chemical reaction is mostly correctly defined as. Before you can even look at the options, you need to remind yourselves on how do you define reaction rate. We know that reaction rate is the change in concentration of the reactants or products per unit time. Now let's look at those options. A time taken for the reaction to occur definitely is not the time taken for the reaction to occur. The speed at which the reaction takes place, which is also not correct. The change in the amount of the reactants or product. This one is closer to the correct definition. However, we know that the word per unit time, if it is not there, then the definition is incorrect. The change in the concentration of the reactants or products per unit time. So you can see that D is our most correct answer in order for you to be able to define the rate of reaction or reaction rate. Now, equations below represent the decomposition of calcium carbonate, which is calcium carbonate decomposing to calcium oxide and carbon dioxide. Which one of the following factors will increase the initial rate of the decomposition of calcium carbonate? So if you look at calcium carbonate, we look at the reactants because we know that the factors must be the factors that are affecting the reactants. And if you look at pressure affects only the gases. So our reactant is a solid. Yes, temperature can affect the rate of our initial rate of reaction because as you increase the temperature, you are increasing the number of the average kinetic energy of reacting particles. Concentration will not affect the rate of reaction because we are dealing with solid, and we know that concentration mostly affect what solution, and mass definitely is not one of the factors that affect the rate of reaction. So the correct answer is B, which is our temperature. Here they say consider the reaction represented by the balance equation below. A plus B give you 2B, which is all a homogeneous reaction, which they are all in the same phases and their gases. The activation energy of the forward reaction is 180 kilojoules, and that of the reverse reaction is 200 kilojoules. What is the change in the delta H? So we know that delta H is going to be what? Is going to be the forward reaction subtracting the reverse reaction. So it's going to be our 180 kilojoules, which is going to subtract our 200 kilojoules. So our answer is going to be minus 20 kilojoules. And minus 20 kilojoules, this one is incorrect. Of course, this one is correct, incorrect, and incorrect. So our correct answer is going to be number B, which is minus 20 kilojoules. Then let's look at our long question again. Here they are saying the reaction between sodium thiosulfate with the molecular formula given and excess hydrochloric acid is used to investigate the effect of concentration and temperature of the rate of reaction. The balance equation for this reaction is given: sodium thiosulfate plus 1 mole of sodium thiosulfate plus 2 moles of hydrochloric acid to give you 2 moles of sodium chloride, 1 mole of sulfur, and 1 mole of sulfur dioxide, and 1 mole of water. An aluminium flask is placed on a white paper marked with a light cross on it. Time taken for the visibility of the crosses to disappear is measured. See the diagram below. So this is the setup of the experiment. As you can see, we have our sodium thiosulfate, and then with reacting with hydrochloric acid, and there's a paper marked as. So we want to see how long will it take for the mark X to disappear. The same volume of sodium thiosulfate solution was used for all the reactions. The table below shows the reaction conditions. So here are the experiment 1, 2, and 3, and all the conditions of the experiments are being shown on the table. As you can see that the concentration of sodium thiosulfate is the same, 0.5 in all the 3 experiments. But when you look at the concentration of hydrochloric acid, you can see that in experiment number 1 is 2, in experiment number 2 is 1, and in experiment number 3 is 2 again. And then the temperature in experiment number 1 is 25 in experiment number 2, and 40 in experiment number 3. And then the volume of all of the hydrochloric acid is the same in all the experiments. The first question says define the term reaction rate. As you can see that now the term is coming for the second time, meaning that it is very important to remember all the definitions that are part of each and every topic. Write down the name of the independent variable for comparison of experiment 1 and 2. So when you look at experiment number 1 and 2, we are going to look at what is it that is being changed between the 2 experiments, because an independent variable is the variable that you change, is the variable that you are going to change in order for you to measure a certain variable. So when you look at the concentration of the thiosulfate between experiment 1 and 2 is the same. However, their concentration are not the same. In experiment 1, we have 2 moles per decimeter cube. In experiment 2, we have 1 mole per decimeter cube. Immediately when you have such a condition, you must remember how does the concentration affect the rate of reaction and which experiment is having the higher concentration. So by the look of the data that is provided, you can see that experiment number 1 is having a higher concentration as compared to experiment number 2. Their temperatures are also the same, and also the volume of the hydrochloric acid is also the same. So what is our independent variable here? Our independent variable here is the concentration of what? Is the concentration of HCl in both experiments. It is not going to be correct to just say it's a concentration, because we are also given the concentration of sodium thiosulfate and is the same in these 2 experiments. So you must specifically say which concentration is different. And the only concentration that is different is the concentration of HCl in the 2 experiments. So it is very important to write that concentration of HCl is the one that is different for 1 mark. How will the amount of sulfur formed in experiment 1 compare to the amount of sulfur formed in experiment number 2 at the completion of the reaction? Definitely, we know that the higher the concentration, the more the number of particles per unit volume. So we expect the number of particles of sulfur to be, they choose from higher than, lower than, or the same. So we expect the concentration of the amount of sulfur to be higher than, because we know that the higher the concentration, there will be more, but it will increase the number of particles per unit volume. There will be more particles with sufficient energy greater than or equals to activation energy, and there will be more effective collision per unit time. So you need to explain how does the increase in concentration increase the reaction rate or affect the amount of particles that will be formed during this reaction. Then the Maxwell-Boltzmann curve, energy distribution curve for experiment 1 and 3 is shown. Immediately when you see the curve or the graph, already you need to recall and come up with a conclusion to say which graph represent higher temperature and which graph represent lower temperature, because this is the temperature graph. So you can see that graph T1 indicates a lower temperature, and graph T2 represents a higher temperature. So we are comparing between experiment number 1 and number 3. So they say which experiment 1 or 3 represented by T2. So we expect a graph T2 to represent a graph or an experiment with a higher temperature. So we are comparing experiment number 1 and number 3. And if you look at temperature of experiment number 1 is 25 and of temperature number 3 is 40. So definitely you can see that the temperature of experiment number 3 is higher than the temperature the experiment number 1. Therefore, it means the curve T2 represent a higher temperature, which is experiment number 3 for 1 mark. Explain the answer in question 5.4.1 by referring to the collision theory. Remember, I told you that collision theory must be used in order to explain how does each factor affect the rate of reaction. So we need to recall. You can just go back and just recall the bullets on how does a temperature affect the rate of reaction. We know that temperature number 1, it increase. What does it do? It increase the average kinetic energy of reacting particles. That is the first bullet on how will the temperature, the increase in temperature, affect the rate of reaction. Number 2, there will be more particles with sufficient energy, which is our kinetic energy, of course, energy equal or greater than activation energy. Activation energy. And we know that there will be more effective collision per unit time. So these are the factors that you need to gather before you start to answer or to respond to the question. So because it's 3 marks, definitely the examiner will expect you to write 3 facts about how will the increase in temperature affect the rate of reaction. So the first thing is that they increase the average kinetic energy of the particles. There will be more particles with sufficient energy, which is equals to or greater than activation energy, and there will be more effective collision per unit time. So the explanations that we have given, they definitely qualify for 3 marks. And then sketch the graph sketch the curve T2 only on the answer book and indicate the effect of a catalyst in this graph. You know, when you draw a catalyst, you expect that the catalyst will do what? Will lower so the activation energy now will be low because it will be lower. We know that it provides an alternative a pathway of lowering activation, and so this will be your X, which is your which indicates the adding of a catalyst, and this one will be your activation energy. So the graph will be a little bit lower as compared to what it is originally. Okay. Now another question, it says the zinc granules are added to 100 cubic centimeter of 0.2 mole of hydrochloric acid solution in this flask. The equation for the reaction that takes place is zinc plus hydrochloric acid give you zinc chloride plus hydrogen gas. So you are provided with a reaction, you are provided with the information about zinc granules, which you are given the volume of zinc granules and also the concentration of HCl. Now they say, okay, here is the mixture inside the flask, and we can see that there are bubbles of gas forming, going out, and also this is the concentration of hydrochloric acid, and these are the zinc granules. Here they say the rate of the reaction is followed by measuring the loss of mass of the flask and its content at gradual time intervals. After completion of the reaction, it is found that 0.12 grams of zinc granules did not react. Immediately when they tell you that there is some part of the reactors that didn't react, already the examiner is giving you an information about your excess and your limiting reactant. So you can see here that our zinc will be our excess reactant, meaning that hydrochloric acid will be used up. So for any calculation in terms of the mole ratio relationship, we can't use zinc, but we'll definitely use what? We will use hydrochloric acid because zinc is in excess. Now, let's look at the questions. Which reactant is a limiting reactant? As I was just explaining, from, let me just go back. From the information that we are provided by the examiner, we are told that there is a certain amount of the mass of zinc that remains. So that is the one that is telling us that zinc is in excess. So it means our limiting reactant is going to be what? Is going to be a hydrochloric acid. So it is very important to read the entire question for you to understand what is it that you are dealing with. It says, give a reason for the loss of mass of the flask and its content, and is for 1 mark. Now, from the statement, we were told that as they were measuring, there was a loss of mass on the flask and its content at the regular intervals. So it means there was a change in mass and the mass was decreasing. So the question is, what is the reason of the decrease in mass? We can see that this, number one, is an open system. Meaning that if you are saying it's an open system, there is an interaction between the system and its environment. So it means not all the contents inside the flask are kept inside. And it means that some chemicals can go out, some chemicals can go in. The system is not isolated from its environment. So it's an open system. So we can see that now the volume, as the gas is formed, which is our hydrogen gas, the hydrogen gas is escaping. So because the hydrogen gas escape, it shows that definitely the mass will decrease. So the reason why the mass decreases is because of the escape of hydrogen gas from the flask. And then the next question says, sketch a graph of mass of zinc versus the time for the above reaction and label the graph P. Why is it important to understand the change in the concentration or in the mass or in the moles of reactants and product? When we started, we said the rate of reaction is the change in the concentration of the reactants or products per unit time. So immediately when you need to draw the graph of zinc, the first thing you need to ask yourself is that is the zinc a reactant or a product? And you can see that zinc is our reactant. Zinc and hydrochloric acid, they are our reactant. Therefore, we expect the decrease in mass. We expect that the mass of zinc decreases as the reaction progresses. So we know that as we are going to draw the graph of mass of zinc versus time, we in grams, of course, versus time, we expect the mass of zinc to decrease. And there is no way that our a graph can touch the 0 point, because which we are going to name it P, because there is an excess reactant that is remaining. So there is some mass that will remain, the mass of the beaker and the mass of the mass of zinc and the mass of the beaker. So that is why our graph will not reach the 0 point. It will just stop before 0, because there is a certain mass that will remain, which is the mass of a zinc, which is 0.12 grams, and also the mass of the beaker. So that is why our graph doesn't touch 0. Then they say here, on the same set of axes in S question 2.3, sketch the graph of Q now, which represent the same reaction at higher temperature. Now, in terms of the temperature, we know that as we increase the temperature, we expect the reaction rate to increase. And as the reaction rate increases, it means now we will compare the two graphs in terms of their gradients. We know that if we are now having a high temperature, we'll expect the graph to be more steeper than the first one. And it will be also below the first one, because it means now it will occur at a higher rate. So when you look at the two graphs, because they are on the same set of axes, the graph Q will be more steeper than graph P, and the two graphs will end at the same time, because the same amount of zinc, the same amount of of a gas will be collected, and the same amount of zinc that is left will be the same. However, the steepness of the graph Q will be higher than the steepness of graph P, and also the two graphs will end at the same point because of the same mass collected for the two same mass, which is going to be of zinc granules, which is going to be at the end of the reaction. So but the only thing is about the steepness of the graph. So you can see the graph P is going to be most steeper gradient, and also a P joins afterward after Q. And then let's go to the other question. I think this one is the question about the calculations. Use the collision theory to explain why Q differs from P. As you can see that now, as we are using collision theory, is about the higher temperature. So the higher temperature, we collected all the facts about what happens at the higher temperature. At the higher temperature, there will be an increase in the average kinetic energy of reacting particles. That is the first thing. So there will be more particles with sufficient energy that is equals to or greater than kinetic energy, and there will be more effective collision per unit time. So even if you said increase in temperature increases the average kinetic energy of reacting particles, that is the first thing that you're going to mention, because that is what the temperature do as you compare it with other different factors that affect the rate of reaction. And also there will be more particles now with sufficient kinetic energy, or kinetic energy is equals to, which is greater than or equals to activation energy, and there will be more effective collision per unit time. So there is no other way of explaining what makes the temperature to be different except using the collision theory. So we are going to use the collision theory to explain any change that occurs in the reaction. And then the last question says, calculate the mass of zinc initially present in the flask. When you look at, already we know that our zinc was our excess reactant, and we are told that 0.12 gram of zinc was left. So we want to know what is the amount of zinc that was used in order for us to combine with what is left to find the initial amount of zinc. So you need to interpret this to say it means we must find the mass of zinc used and add the 0.12, which is our excess, in order to find the initial mass of zinc in the reaction. So what information do we have? We have the information about we are going to add a zinc granules are added to 100 cubic centimeter of what? Volume of HCl. So there is more information about HCl that is given to us than the information about zinc. And we know that the HCl is reacting with zinc, and HCl is a limiting reactant, as we've identified. So if we can find the number of moles of hydrochloric acid, we will also be able to find the number of moles of zinc that will react with that hydrochloric acid using the mole ratio. So we know that hydrochloric acid and zinc, they react in the ratio of 1:2. So immediately when you can find the number of moles of hydrochloric acid, they will assist us to find the number of moles of zinc that will react. So we're going to start and find the number of moles of hydrochloric acid, which is the limiting reactant, and we're given information about our limiting reactant. So the number of moles of hydrochloric acid, they gave us the concentration of hydrochloric acid and also the volume of hydrochloric acid. Remember, it was 100 cubic centimeter. We are going to divide it by 1,000 for us to get how much? 0.1 cubic decimeter. Cubic decimeter, because we know that volume is measured in cubic decimeter. And we know that if the concentration is 1 mole decimeter cube, then definitely we need to convert our volume into cubic decimeter. So we are going to find the concentration is going to be substituted, and then we're going to find the number of moles of our limiting reactant, which is hydrochloric acid, that reacted with zinc, so that we can find the number of moles of zinc that will react with hydrochloric acid. And the number of moles of hydrochloric acid that we get is 0.2 multiplied by 0.1, and we get 0.02 moles of what? Of HCl. After getting the number of moles of HCl, we are now going to use the mole ratio. Remember, the mole ratio will always be assisting us because we are taking it from the reaction itself. So how is zinc reacting with hydrochloric acid? Zinc with hydrochloric acid, they react in the ratio of 1:2. Therefore, if this one is 0.02, then this one is going to be X. So we're going to find, which means it's going to be 0.02 divided by 2 because it's the half. So that is why here we are saying the number of moles of hydrochloric acid, we have them so that we can find the number of moles of what? Of zinc, which is going to be 0.01 as you are using your calculator. Remember, it is very important that you are getting used to the calculator that you are using every day so that you can be able to operate it correctly to prepare yourself for examination. So now we are going to find the number of moles of zinc, which is going to be 0.01 mole of zinc. However, the question is not looking for the number of moles of zinc, it's looking for the mass. So we need to know what is the mass of zinc that reacted with hydrochloric acid. So if we find the number of moles, we know we are going to use the formula N is equals to M over M of zinc. The number of moles we already have is 0.01, which is equals to, we don't know the mass, but we know the molecular mass of zinc. Where do we get it? We get it from the periodic table. Let me just use it here. It's going to be N is equals to M over M, which is going to be 0.01 is equals to M over 65. So where is the 65 coming from? The 65 is coming from the periodic table because this is a atomic mass of zinc. And then we are going to find the mass of zinc, which is going to be 0.65. So the 0.65 is the mass of zinc that reacted with hydrochloric acid. Is not the initial mass of zinc because we were told that zinc is in excess. So after getting the mass of zinc that reacted, we are going to take the mass of zinc that reacted and add the mass of zinc that is in excess. As I said, that we need to find the mass of zinc that will be used, and add 0.12 that is in excess for us to find the initial mass of zinc. So from there, you can see now that from the mass of zinc that we got, which is 0.65, we are going to add 0.12 and find 0.077, which is the total mass of zinc that is. So for stoichiometric calculations, you know that you need to make sure that you understand the question and also use all the skills of calculations in order for you to get the correct marks. Just to recap, because we have come to the end of the lesson. From the start, we look at the definition of rate of reaction. We look at how do we calculate the rate of reaction, especially looking at the difference of how do we calculate the rate of the product and the rate of the reactants, whereby when we calculate the rate of the reactants, we look at the issue of a negative number that we are going to use in order for us not to get a negative number. And we also look at the factors that affected the rate of reaction. We emphasize on the factors that will increase the rate of reaction. The factors were temperature, concentration, catalyst, pressure. And in terms of pressure, it's just like when we are increasing the concentration, because when we are increasing pressure, which is the one factor that we never even look at it because it's just as same as the concentration, you are also increasing the number of reacting particles, because as you are compressing pressure, you are making particles to be more in that container. And we need to also know, how do we increase pressure? We only increase pressure by doing what? By decreasing the volume, or decrease pressure by increasing the volume. So in this case, because we will look at the factors that increase the rate of reaction, we are going to look at how are we going to increase pressure in order for our reaction rate to be higher. We also look at the addition of a catalyst and also increasing in the surface area. All the factors that we look at them by making sure that we use collision theory to explain each and every factor. The examiner will definitely give you the experiments or different comparison experiments so that you can see the changes in those experiments and be able to compare the factors that affect the rate of reaction. So it is very important to know how does each factor using a collision theory affect the rate of reaction. And also, there are lots of stoichiometric calculations that you can expect as you are dealing with rates of reactions. And when we look at our calculation techniques, we will always check our limiting reactants and our excess reactants. And we know that immediately when you find your limiting reactant is the one that you are going to use as your mole ratio to find your moles of the excess reactant. And from that is then that you can solve what you are looking for, because the examiner will normally give you one of the information of the reactant or product and expect you to use that in order to find the other one. We have come to the end of the lesson. Thank you so much for watching today's lesson. I wish you all the best as you are preparing for your final examination. From my side, thank you very much and goodbye.